It's my pleasure to introduce our next speaker. Dr. Becca Thomases is a full professor and vice chair of graduate studies in mathematics at the University of California, Davis, UC Davis. Dr. Thomases uses tools from analysis and numerical simulations to study fluid dynamics in complex or non-Newtonian fluids. Recently, she's been looking at how microorganisms such as sperm and other flagellated organisms move in mucus and other sticky, gooey environments. In addition to mathematical research, Dr. Thomases spends a lot of time working on diversity, equity, and inclusion efforts in graduate and undergraduate education. She led an initiative to introduce undergraduate learning assistants in calculus discussion sections to facilitate active learning environments. She also modernized the graduate teaching assistant training course at UC Davis to incorporate lesson plans that specifically address topics such as understanding the role of diversity in classrooms and developing concrete strategies for building inclusive classrooms. As a curricular dean, this warms my heart to see how you can use curriculum to make effective change. Dr. Thomases was one of the plenary speakers at the first Spectra Research Conference this past August, hosted online by the Institute for Computational and Experimental Research in Mathematics, or ICERM. Spectra is an association for LGBTQ+ mathematicians. During that presentation, Dr. Thomases thanked her wife and children for their love and support in helping her to do all that she does. And with that note, I will pass the baton to Professor Thomases.
Thank you very much. So let me just get my screen share going here. Okay, so can you all see my screen? Hopefully.
Yes, you're good to go, and you're spotlighted. So.
All right, thank you very much. All right, thank you. So first, I'd like to thank the organizers, Anthony Bonato, Juliette Bruce, and Ron Buckmeyer for organizing this fun day. I'm really happy to be here, and I'd also like to thank the Fields Institute for hosting the event. And I always like to thank UC Davis and the Davis Mathematics Department, as well as the National Science Foundation for their ongoing support of my research. And here I am with my same slide from the ICERM talk. But before I discuss my research, I do want to spend a couple of extra minutes introducing myself. As I said, I'm a professor at UC Davis, and I've worked in the math department for the past 15 years. Davis is something I learned recently. A lot of people don't know where Davis is, so I like to tell people. It's situated near the capital of California, which is Sacramento. We're about an hour and a half away from lots of really amazing sites in California, such as San Francisco and Lake Tahoe. Davis is a quiet college town with a lot of bicycles. And the UC Davis Mathematics Department has actually two graduate programs, the math program, which I'm currently the chair, and as well as the graduate group in applied math, which I'm a member of. So please do reach out to me to ask me more about our graduate program. We're always looking to admit an excellent, diverse graduate student body. And so finally, I'd like to acknowledge a few other people that support my research and keep me whole. I met my wife, Kyung, when I was in graduate school at UC Santa Barbara, and she has traveled across the country with me many times now through my postdoc, my job at Davis, 2 sabbaticals, one when my older son was only 2 months old. We have 2 boys, Henry, who he's like 11.99. He turns 12 on Saturday. I can't believe it. And Walden, who's 9. Our first baby is our very old dog, Charlie. She's a Havanese. She joined our family when I was a postdoc. At that point, I was not quite ready to have kids. Anyway, so with thanking all of these people, I'll now turn to the main motivation of my talk, which is human health. Fertilization. So certainly fertilization is crucial to human health. For successful fertilization, the sperm must navigate through complex geometries such as the fallopian tubes and complex materials such as mucus to get to the egg. And cilia beat in our lungs. This beautiful movie is not of the lungs, but cilia beat in our lungs to move mucus for healthy lung function. And understanding how these cells and organelles move in different fluids or materials could help scientists design tools for sperm selection to increase success of fertilization or help the diagnosis of debilitating diseases such as emphysema and bronchitis, which are thought to be related to poor ciliary function. I'm going to talk today a bit about how applied mathematicians such as myself model these types of systems, which involve a swimmer or organelle and a fluid. The swimmer is active, it uses energy to move, and the fluid is typically non-Newtonian. We'll talk more about what that means later. Studying biological and physical experiments can be crucial in the development of our mathematical models because the choice of the model depends on the question we're trying to answer or whatever hypothesis we're testing. I'm going to start by talking a little bit about swimming at small spatial scales, a somewhat non-intuitive regime for us. And then I'll talk a little bit more about non-Newtonian fluids. And finally, I'll talk about how we put these two together and how do we construct a mathematical model. And finally, I'll describe some of the interesting things we've discovered about how to swim through goo. So let's look a little more closely at what it means to swim. A definition suggested in the 70s by E.M. Purcell in a famous talk on low Reynolds number locomotion is that to swim is just to be put in a liquid and you're allowed to deform your body in some manner. We typically think of swimming via a swimming stroke, which we are all familiar with on the macroscopic scale, like we see the swimmer here. But on the microscopic scale, cyclic deformations or strokes are performed by bacteria or other swimming cells to translate from point A to point B. Now, as I said, we're more familiar with the macroscopic scale where we can take advantage of inertia or gliding, which helps us move without continuously moving our body. Now, at the microscale, this is not how things work. So we think about how to think about things at the microscale. It's very helpful to define first an important non-dimensional parameter, the Reynolds number. And this is the ratio of the tendency to glide, inertia, to the viscous forces, which are the things that stop us, the friction and the friction in the fluid, right? So it's related to the viscosity. So this is defined as the ratio of the fluid density, characteristic velocity, or length scale, divided by the viscosity. So if the fluid is sticky or you are small or very slow, then the Reynolds number is small. And in this regime, all the forces are at equilibrium. The equations of motion for Newtonian fluids are given by the Stokes equations down here. We see, in these approximations that the humans swim at high Reynolds number, but sperm and bacteria are down here in the low Reynolds number regime. Now, so if the motion is just given by deforming the body, a microorganism must keep moving to translate. If they stop deforming their body, they stop moving in a Newtonian fluid. And here in the Stokes equations, I'm going to use this F to represent the forces that are acting on the fluid that come from the body motion. They're basically boundary conditions. When the body moves in the fluid moves in response to that motion. So here are some of the organisms that move using flagella and cilia. We have E. coli and paramecium. And these are on the orders of tens to hundreds of microns at low Reynolds number. And they move by generating beats with their flagella or cilia. Flagella are well conserved across species, meaning this 9+2 structure here that you see with these little dots, this arrangement of what's called microtubule doublets is found in both eukaryotic and prokaryotic organisms across a wide range of these microorganism species. And in these flagella, there are dynein motors along the flagella. And the beats that they generate are a result of reactions between the fluid, elastic forces in the bending filament, and motor activity along the flagella. So a key question we're looking at today is how do these beats change or interact with the surrounding fluid? Because it is known that different beats are found for the same organism in different fluids. So this is just some pictures from my collaborator at UPenn, Paolo Arratia, who has taken data for tethered mice sperm in various fluids, and the fluids range from a buffer solution water to viscoelastic fluid, which has some long chain polymers adding fluid elasticity, and then a higher viscosity viscoelastic fluid. And you see some differences that you can notice to the eye in the types of the wave patterns, in particular, the symmetry of the wave, of the flagella. These are the flagella over a whole bunch of periods. The symmetry is broken here in the viscoelastic fluid, and yet again, in a different way for the higher viscosity. So anyway, so how do we set up a numerical simulation that can faithfully represent some of these features to figure out how to swim in a viscoelastic fluid? So that's what we're going to talk about. But first, I want to talk a little bit more. So we talked about swimming. So now let's talk about viscoelastic fluid. What is this goo? I'm going to show a short video of some familiar materials, starting with water. And after that, I'll discuss some observations about these materials that will help us understand how to define a viscoelastic fluid. So just watch this video. I'll kind of talk you through what you're seeing. We've got water and a rubber ball, a racquetball ball, a memory foam pillow. That's my pillow right there. Silly putty, and I'm going to just play with the silly putty at sort of different rates, pulling it apart. I could actually do this here. I've got my silly putty up there. But if I try to do this, it's very messy if I have to like play with hair gel in front of you. So this is hair gel kind of hanging on the top of my hand, and I'm gonna rub it between my hands just to see that it flows really smoothly. This is toothpaste coming out of the tube. And one thing to notice is it's a very tubular shape as it comes out. It really holds its shape. Here's an egg. I'm playing with the egg white, and you can see here that the egg white, you can pull it apart between your fingers. I'm not the best cameraman, so it's a little out of focus. But notice there's a little droplet that kind of falls right then. And then this is, you know, a really fun thing to play with, the cornstarch and water. Definitely goo. Here, you can see that when you really push on it, and I'm sure most of you, if not all of you, have played with cornstarch and water. If you push on it, you get a solid-like material, but if you like kind of just let it rest, it just kind of melts in your hand and it flows like a liquid. So that's the last material I played with. So we saw that water, it doesn't keep its shape, it flows. And in the rubber ball, it returns to its original shape after deforming it. The memory foam pillow can sort of remember that deformation on a short time scale, but on a longer time scale, it kind of goes away. And the silly putty has these different types of behavior depending on the rate at which you pull on it. Hair gel can stay up in your hand upside down for a little bit, but it does spread easily. The toothpaste that has this tubular shape but comes really easily out of the tube. And if you've ever thought about why that is, like how is that possible? Eggs can hold together, they really can stretch between your fingers, and then the cornstarch and water is like a liquid, but also like a solid and with this pressure. So what's going on? So what are some of those properties? Well, the one I want to think about with the fluid water, it has a resistance to flow. This is the fluid viscosity. So there's a relationship between the rate at which you pour things and how quickly they come out, and that's related to the viscosity. So if I was playing with honey, which I didn't happen to have at the time, it would be very hard to pour that out. It takes a lot longer. Rubber ball is an elastic solid that has a kind of a plastic shape, or sorry, like a set shape that you can deform, but it always comes back to that shape. Where the memory foam is sort of in between. It will deform for some finite amount of time, and then it will go back to its shape. Silly putty is a complex material with both fluid and solid-like properties. And then the hair gel with this ability to thin with the external shear. And that's exactly what's giving toothpaste its ability to flow out of the tube really easily, but stay in its tube shape because it's shear thinning. So you feel this, you experience this extra shear as you move along the edge of the tube. The egg is the most viscoelastic of the materials I looked at. So that's really what you want to have in your head when we talk about the properties going forward. And it exhibits what we call a bead on a string instability, which you can see a little bit more clearly in this figure from a paper, where they're looking at stretching of a viscoelastic material between two plates, and you see these little beads forming along. And you can actually do this yourself, at home experiment right now with a little bit of saliva. Your saliva should have a little bit of mucus in it. You can stretch it apart in between your fingers and see sometimes that little bead on a string instability. And since we're all in our own spaces now, you can do this right now as we're talking. Usually during a talk, I tell people to wait until later to do this, but cornstarch in water, this is shear thickening. And so this is the opposite of the shear thinning of the hair gel, where you actually add an external shear and it gets more viscous. So what's a viscoelastic fluid? I said it's like most like the egg. It has both a viscous and elastic property. It flows like water, but it can remember a shape for some characteristic time scale. So think of the memory foam there. Viscoelastic fluids also have an important property called non-zero normal stresses, which leads to this phenomena such called rod climbing. And you can see this at home as well. If you ever bake a cake, when you turn on your beaters, the cake batter will kind of climb up the rotating beaters, coming probably from the eggs. And anyway, viscoelastic fluids are typically made by taking a Newtonian solvent like water and adding some sort of long chain polymers. And I think of them as rubber bands, although obviously not rubber bands exactly. So a simple model for a viscoelastic fluid is called the Maxwell model. And you can derive this model from a linear arrangement of a spring and a dashpot, and where the spring represents the elastic part of the fluid, and the spring relationship between stress and strain is coming from a Hooke's law type situation where the stress is linearly related to the strain with this coefficient I'm calling E. For the elastic modulus, and then a viscous fluid has a linear relationship between the stress and strain rate. Here, the viscosity mu here is the constant that represents kind of this speed at which something is flowing, right? So we recognize the viscosity in a fluid, motor oil is more viscous than water. We recognize this when we move it from place to place. So we're looking at this dependence on a strain rate. So for the linear arrangement, when I say linear arrangement, we're assuming that the stress is fixed, so tau S equals tau P, but that the strain is additive. So epsilon, the total strain epsilon here is going to be epsilon S plus epsilon P. So by differentiating this equation and rearranging things, you can derive an ODE. And so what this is telling me is that it's not a linear stress-strain relationship anymore. We have an ODE that describes the stress-strain relationship. And I'm going to think in my models of this strain rate as given, and then you solve this ODE to figure out what the stress is. Now, that's a very simplified model. And of course, in a three-dimensional fluid, we need a PDE model, partial differential equation. And so the model I use is called the Stokes-Oldroyd B model, but it really is almost as simple as taking the Maxwell model and sticking it into the Stokes fluid. And so the Stokes equation, if you recall from some slides ago, this is the equations of motion for an incompressible Newtonian fluid at 0 Reynolds number. And we're going to add an extra force. So we can have the external forces coming from maybe the boundary conditions on the body, but I'm going to add an additional force coming from the stress. So the divergence of the stress gives you a force. And this stress evolves according to this ODE. And I'm going to put the ODE in quotes because now we're no longer taking a simple time derivative. Now we actually are going to take a time derivative of the tensor along streamline. So U is this velocity, and if we think of it for a moment as fixed, then all this complicated nonlinear PDE is saying is evolve the tensor along these streamlines, and it has to rotate and follow the flow. So that's why you get some interesting nonlinear terms, which do cool things in the equations. This relaxation time, this is this ratio of this viscosity to this modulus, lambda. So we've really got lambda tau dot, this is all tau dot, plus tau equals mu times. Now this is my new strain rate. In the case of PDE, it's the strain rate tensor, which is related to it's the symmetric part of the velocity gradients. So take this model, put it in there, you get the Stokes-Oldroyd B model, which I'm literally writing again, except now I've got some extra notation to say we have two different viscosities. We've got the fluid viscosity and the polymer viscosity. We have the polymer stress, which evolves according to this PDE, and maybe some external forces. So this whole PDE is the model for sort of the simplest closed continuum model for a viscoelastic fluid. And the important dimensionless parameters are the Deborah number, which is a ratio of relaxation time to a characteristic flow time, and then the fluid modulus. So I'm going to talk briefly about two different methods we use for simulating swimmers in a viscoelastic fluid, after which I'll tell you two short stories about what we learned about swimming in goo from exploring these models. Now, the method we choose depends on the question we're trying to answer. For example, the simulations on the left would show a 1D filament representing a flagella or even a swimmer body, perhaps, moving in a background fluid. We wanted in those simulations the emergent shape to be a result of fluid structure interaction, meaning we could allow that the body, if it was soft, would actually try to avoid maybe regions of higher stress. And we do this by a penalization method where this penalization parameter actually acts as both a numerical parameter as well as a sort of physical parameter related to the body stiffness. We've also wanted to do simulations with a prescribed gait, which you can think of as an infinitely stiff version of the penalization method. And here I'm showing an example modeling a Chlamydomonas algae swimmer. And there we have a 3D body and symmetric and planar 1D flagellar arms in a surrounding 3D fluid. All I'm showing in both these videos is the color field represents the elastic stress. And in both these cases, the motion of the swimmer is coupled to the fluid by computing the forces that the body puts on the fluid. This can be done in a variety of ways. We use variations of the immersed boundary method, which is a popular numerical method for studying fluid structure interactions. So with this in our mind, we can now go to the short stories about the swimmers. And the first one's going to be about the soft swimmers. So here's the puzzle. Does fluid elasticity lead to speed ups or slow downs? Some years ago, there were some seemingly conflicting results in the literature relating to how fluid elasticity might affect swimming speed. And one particular example of this conflict can be seen by looking at the swimming speed of a swimmer in a viscoelastic fluid relative to the speed of that same swimmer in a viscous fluid. So this normalized swimming speed is plotted here on the left for results from simulations, of finite length undulatory swimmers with large tail amplitude. And in this paper, they pointed out that swimming speed could be enhanced by viscoelasticity. So here's an enhancement, a moderate enhancement, about 20 to 30%. This normalized swimming speed goes up and then it goes back down. And so this was a non-monotonic, maybe mild enhancement, 20% speed boost. And you can see that by Deborah number 5, this Deborah number, recall, is that relaxation is a normalized relaxation time, or the non-dimensional relaxation time. By the time you get to a longer relaxation time, you actually start slowing down. And so you can see here that by comparison, the Deborah number 0 swimmer is 5 swimmer is a little bit behind the Deborah number 0 swimmer, whereas the Deborah number 1 swimmer is way up ahead. So now on the right, I'm showing results of a physical experiment by a group, Espinosa, Garcia, Lauga, and Zenit. And they put a microscopic swimmer in a viscoelastic fluid that had a flexible oar for a tail. So this was a physical experiment. And in this experiment, they found a monotonic speed up beyond the sort of low Deborah number that nearly doubled the swimming speed. Now, both groups actually acknowledged in their papers that shape changes were seen in the different fluids. So in other words, they weren't exactly the same stroke. So are we really comparing things fairly? But in neither case was the significance of those shape changes explored. And in fact, it's kind of funny because in this paper, they specifically said, oh, look, those shape changes, they're really small, right? I see that the red guy, I think, is the viscoelastic, the blue guy is the Newtonian. Oh, those are pretty small changes. And again, you see changes here in this tail, okay, from Deborah number 5 to Deborah number 0. Those are small changes. But finally, I'll point out that the biggest difference between these two experiments is how they vary the Deborah number. So in the simulations, they varied the Deborah number by changing the relaxation time. But in the experiments, it was the frequency of the oscillation that was varied. And of course, in a simulation, it's easy to vary either to vary the Deborah number. So to test out kind of what the heck's going on here, we did that. And as we see here, so in this graph, we can see that by varying the Deborah number 2 different ways, we got very different results. So your system can't do that. That doesn't make any sense unless you're missing something. And so what we're missing here was an important timescale related to the body stiffness. So if the body is soft, fluid structure interactions can affect the shapes. There's a timescale that relates to the stiffness of the swimmer. And that time scale is sort of hidden in our numerical methods in this penalization parameter I talked about really briefly. But we can see it more clearly if we look at sort of a balance of elasticity to the hydrodynamics, fluid drag, beam stiffness here. And so you can non-dimensionalize this expression and get a non-dimensional, what we refer to as an inverse body relaxation time, which relates the period of oscillation to the beam memory time. So in R, this L is just the length of the beam, that's the viscosity of the fluid, and this B is related to the numerical stiffness parameter. And in our problem, and say in the flexible ore experiment, it would be related to this stiffness of that ore, which has to be flexible in order for this to swim. So this G here depends on the period, right? And so if you vary the Deborah number by varying the period, you are also varying G. However, if you're varying the relaxation time for a fixed T, you can keep this G fixed. And so that right there really is the difference between those experiments. But well, that's great. So it's great to know there should be a difference. And of course, but why were the results so different? Like what makes this so much bigger than this, right? So for that, we wanted to check out, so we wanted to see what effect this body time scale, this G, what effect does that have on swimmer shapes and then the resulting motions? And so we used asymptotic analysis to predict the shapes, the changes in the shapes due to fluid elasticity and body elasticity. And we found that it predicts soft swimmers in this low G regime here. The amplitude of the swimmer is actually larger in a viscoelastic fluid than in a Newtonian fluid. Now, what do I mean by amplitude? Well, one way to see this live is just to look at this movie. If you stare at it for long enough, you can see that the viscoelastic swimmer, which is red, it tracks the target shape in black better than the Newtonian swimmer. Both are soft, so they don't achieve their target. Look, they're floppy. Like that target stroke has a giant amplitude and the actual achieved strokes are darn small. But they're both tracking that target shape at a different kind of rate, right? The red guy is kind of tracking it better. Now this effect goes away as that target is achieved, because then they're both tracking the target, right? And so that is, as the swimmer becomes stiffer, you lose that boost from elasticity, right? It goes away. So you only see that viscoelastic boost in the amplitude for these small, soft swimmers. Now, how does that affect swimming speed? Well, so for our simplified swimmer model, we could actually use the predictions that tell us how the amplitude is affected to calculate a theoretical swimming speed. And we call it the stroke-induced swimming speed. It's the swimming speed of the swimmer in a Newtonian fluid, but with the gait changes. So in other words, just take these exact shapes, this red shape, then this blue shape, and put both of them into a Newtonian fluid, and who's faster? And the answer is going to be that the amplitude boost gives you a speed boost, okay? And so you can see that here, the stroke-induced swimming speed as a function of the Deborah number for the soft swimmers gives you this monstrous speed up. And for the stiff swimmers, as I said, it should give you no boost because there should be, the target is achieved in all of those cases. It's not infinitely stiff, so it's not giving you exactly one, but it's pretty darn close to one. Anyway, so the punchline of this exploration was that the fluid structure interactions between a soft body and an elastic fluid are very important, and they can lead to non-trivial speed boosts. So if you have to swim in a viscoelastic fluid, it may help to be floppy. So I'm going to move to our second story, where I'm going to talk about some work that was inspired by experimental results on the Chlamydomonas algae cell from the Aratia lab. They measured how flagellar strokes change with viscosity and elasticity. I want to draw your attention here to the swimming speed results that show that the speed of the swimmer is in these results, the speed of the swimmer is separated into the speed during the power stroke and the return stroke. So the power stroke is when this guy swims with like a breaststroke motion, when the arms are coming down, and then the return stroke is when the arms are coming back up along the body. And so they go forward a little bit on the power stroke, and then they back up on the return stroke. And hopefully they back up less on the return stroke to actually make net forward progress, right? However, if we look at the normalized swimming speeds, down here, we actually see that viscoelasticity will give you a bit of a boost for large viscoelasticity during the power stroke, but a much bigger boost, and these aren't the same time, this is 1.4, this is 1.6, so a much bigger boost on return stroke. So in other words, you get a boost on power stroke and return stroke, but the boost is larger on the return stroke, leading to a net slowdown in viscoelasticity. Fine. So with our computation, we wanted to know why. With our computational model, with our prescribed shapes, we can analyze the stroke changes separately from the fluid changes. We can change those independently, but you can't do that in the experiment because, of course, in the biological experiment, this as you change the fluid, the swimmer's stroke changes. Okay, so we modeled, we developed a Newtonian and a viscoelastic stroke model from their experiments, and what we saw was that the first big result was that the polymer stress accumulates at the tips of the flagella. That's the place where the largest amount of fluid elasticity is found, an order of magnitude larger than near the body anywhere else. And this was actually a big result. People did not know this before our results. And in fact, people sort of conjectured that there would be a large elasticity in a region near the front of the body where there's a hyperbolic point in the swimming in the streamlines in the flow, but no, it's definitely near the tips. And here there are some differences between the Newtonian stroke and the viscoelastic stroke, but qualitatively the results for the different strokes were really similar. I'm going to dig into the differences in a bit, but the sort of generic thing was that for both strokes, polymer stress accumulates at the tip, and more stress accumulates as the Deborah number increases. You can see that here on this graph below, and the results are also consistent with the experiments where, namely, the speed boost is larger on the return stroke than the power stroke, leading to a net slowdown. So here are some of the slight differences between Newtonian and viscoelastic strokes. Basically, the Newtonian stroke is faster, but the viscoelastic stroke is just a little bit more efficient. There is a lot more elastic stress in the Newtonian stroke than the viscous stroke. So this may be why the swimmer actually modifies their stroke, perhaps in a viscoelastic fluid, to avoid this dramatic stress accumulation at the tips. So, but what is the effect of the accumulated elastic stress at the tips? And here's just a quick thought experiment. If you're swimming at low Reynolds number and you freeze your stroke, what happens? Well, motion stops instantaneously. There's no inertia or coasting. But in a viscoelastic fluid, that's not so. We found that the swimmer would continue moving in the direction it was traveling if you froze the stroke due to the memory of the past deformation. And we quantify this by measuring the velocity at the moment when the stroke is frozen, where we compute a peak coasting velocity. And when we plot this, a coasting velocity in both power and return, we see that it correlates strongly with the speed boost seen in the simulations. So the picture we have so far is that a speed boost due to fluid elasticity occurs on both power and return stroke, and this correlates with the initial coasting velocity due to the accumulated stresses. But it still begs the question, why? Why are the elastic stresses generally decreasing during the power stroke and then increasing during the return stroke? So the clues to the answer for us had to do with two things. One, the fact that the stress accumulates at the tips, and two, the orientation of the tip is different during power and return strokes. We demonstrate that here by just measuring the angle between the swimming direction and the tip, and see that it's closer to perpendicular or normal during the power stroke and tangential on the return stroke. Now, orientation dependence of flagella is essential to how swimmers move at low Reynolds number. So the swimmer is taking advantage of an asymmetric force-velocity relationship. Namely, in a viscous fluid, it takes more force to drag a rod normal to the direction of motion than tangential, which leads to higher velocities on power stroke than return stroke. But what we're seeing here is that the viscoelasticity reduces this advantage. So the take-home message from these clamming experiments was that the elastic stress that accumulates at swimmer tips depends significantly on the orientation relative to the direction of motion. Stroke shapes are very important, and small differences seem to greatly affect swimming speed and efficiency, especially in viscoelastic fluids. So how to swim in goo? To conclude, we saw that elastic stress accumulation near tips of swimmers can enhance swimming speed, but directions matter, and so this can lead to slowdowns or speed boosts. So we don't really have the answer, of course. I'll finish by saying that these mechanisms are only part of the story. There's still a lot to understand, such as the internal dynamics or the active motors inside the flagella and how they interact with the flagella body, because of course, these organisms are active. And finally, I want to thank my co-author and main collaborator, Bob Guy, as well as our former student who worked on the CLAMI project and our experimental collaborators and the National Science Foundation. Thank you very much.